Hello there. In this video, we'll be analyzing the same circuit that we did for the previous two videos, but instead of using node voltage analysis and source transformation, we'll be using mesh current analysis to show you guys how mesh current analysis can be applied to this circuit to find IL infinity. Now, this is a general solution to natural and step responses, but we're looking specifically for currents because we want to find currents through inductors and voltages across capacitors. In this case, this is an RL circuit. We have an inductor and resistors, so we want to find the currents through inductor. Now our tau in RL circuits is L over R Thevenins. We'll need to find R Thevenins later, but first let's define our ground node and define our mesh currents in the clockwise direction. Call that I1, call that I2, call that I3, we'll call that I4. Now remember that we already have our initial current. We need to find our final current for when t is greater than 0. For when t is greater than 0, when time goes to infinity, the inductor stores enough energy that it simulates a short circuit. So it simulates as like a short wire. So essentially this inductor shorts, and we need to find this current through this shorted wire. Okay, now let's start by analyzing our first mesh. What is the mesh current going around this mesh 1? It is simply the opposite of this 3 amp current source. So I1 is negative 3 amps because it's going in the opposite direction. Now I2, we're going to find the mesh current going around I2 in reference to its clockwise direction. So from your ground, we'll go here, and when we're going through resistors, we're always going through resistors from plus to minus in respect to this mesh current, to the direction of this mesh current. So before resistance times its current, I2 minus I1, right? Because the current going through this 4 ohm resistor is a combination of I2 and I1, but it is in the direction of I2, so I2 would subtract I1 plus this voltage across the 6 ohm resistor, plus to minus in reference to this clockwise direction, is 6 times I2 plus, well, I have to find, because we're using mesh current analysis, we're using Kirchhoff's voltage law around these meshes. And what's the voltage across this current source? Well, we don't know, so we give it a name. So we'll give it a variable called V1. And define our polarity as plus to minus. And since this is plus to minus, we're going in the clockwise direction, so we're going a drop. So this would be a drop across this current source. So plus V1 is equal to 0. Go back. Now for mesh 3, we're taking our it's a rise from this current source. So V1 equals to, this is a drop across resistors. Currents always go from plus to minus through resistors, so it'd be 6 times its mesh current, 3. And now for mesh 4, from ground, we're going up, going plus to minus through resistors, from plus to minus in reference to this mesh current. So we have 12 ohms times its mesh current, I4, plus, going across, this is a drop across this voltage source, so plus 12 volts, equal to 0. Okay? Now, remember that we're trying to find IL, the current through this inductor in this direction, going down. Now, IL is a combination of I3 and I4, but in the direction of I3. So keep this in mind that IL is equal to I3 minus I4, and that'll be the direction in IL, in the direction that's going downwards. Now, we can solve I4 pretty fast. So I4 is one variable. I4 is equal to minus 12. Oh, sorry. This is actually not 12, 20 volt voltage source. So 20 minus 20 divided by 12 volts. So we have negative 1.67 amps going in the clockwise direction for this mesh, for mesh 4. Now, we already solved for I1, negative 3 amps. We solved for V1, so we can plug these two equations into mesh 2's equation. So we'll have, let's see, 4 I2 minus 3, so plus 3, plus 6 I2 plus 6 I3 is equal to 0. Okay, now let's simplify this equation right here. So we have 4 I2 plus 4 times 3 is 12 plus 6 I2 plus 6 I3 is equal to 0. And so 4 plus 6 is 10 I2 plus 12 plus 6 I3. Okay, so look, we have one equation but two unknowns. So that means we need another equation that has I2 in it and I3 in terms of I2 and I3. Now remember when we declared our variable V1 across this current source? We'll need to write an equation, this equation in terms of I2 and I3. And if we look at 6 amps goes up and it splits. So 6 amps is a combination of I3 and I2, but in the direction of I3. So remember that. Okay, so our equation is 6 amps going up in the direction of I3. So I3 minus I2, current that's impeding it, is equal to, this is our second equation, so we can plug, so if we can plug this equation, if we simplify it, into this equation. So let's add I2 to both sides, so that equals I3, and we plug I3 to here, and we'll solve for I2. So 10 I2 plus 12 plus 6 times 6 plus I2 is equal to 0. Plugging this I3 into here, and we'll simplify this further. I2 plus 12 plus 36, 6 times 6 is 36 plus 6 I2 is equal to 0. Okay, now we have 10 plus 6, so we have 16 I2 and plus 12 plus 36, 48 is equal to 0. And we'll solve for I2. I2 is equal to negative 48 divided by 16, and we have negative 3. Okay, so I2 is negative 3. We have solved for I1, we have solved for I4, and now we can finally find what IL is. You see IL is I3 minus I4. What is I3? What is I3? Well, we've solved for I2. Now we'll solve for I3. So what is I3? We have 6 plus I2. 6 plus I2 using this equation up here is equal to I3. So we have 6 plus, substitute, -3 minus 3 is equal to I3. So 3 amps is equal to I3. I3, okay? Now that we have 3 amps, so I3 is 3 amps, so minus I4. What is I4? We found it down here. Minus I4, so I4 is negative 1.67. So minus 1.67. And we'll see that IL is actually 4.67 amps. That's this current going down in this direction. That's our I infinity for t greater than 0. Now we'll just plug it into this equation, our general equation. Okay, let's just do that here. So we have I of t, IL of t, current through the inductor, is equal to final current 4.67 plus our initial current 3 minus our final current minus 4.67 times e to the minus t over tau. Now tau is L over R Thevenin's. Our Thevenin's, we can find this easily. I think I did this in the last video. Now what we do when we have independent sources, when we only have independent sources in our circuit, we can take a shortcut by zeroing out our independent sources by zeroing out voltage sources by shorting them, zeroing out current sources by opening them. And let's redraw this equation, this circuit right here. So when we're finding our Thevenin, zero out your independent sources. So 6 ohms, we have 4 ohms, and we have, so this current source would pop open, and 6 ohms, and we have, oh, and don't forget to remove the load. A, call this B, and we'll call this 12 ohms, and this 20-volt voltage source is shorted, so this will short. So what's the resistance seen from A to B? Well, you have the 6 ohm resistor in series with 6 and with 4, and in parallel with 12. So we have 4 plus 6, 10 plus 6 is 16 ohms in parallel with our 12 ohm resistor. Okay, and if you remember how to do this, simplify our equivalent resistance. 16 times 12 divided by 16 plus 12 is equal to 6.85 ohms. That's our Thevenin's. And now we need to divide our Thevenin, L, our inductance. We have 0.4 henries, so 0.4 divided by 6.85 equal to, we have 0.058 seconds. And now we just plug, that's tau, and we just plug tau into there. And once we have that, we'll have our final equation for t greater than 0. And this answer should look the same as our previous 2 videos. But in this video, we're using mesh current analysis. So thank you for watching.